So you got the list there. Just a quick overview, a trig identity is an equation involving trig functions that is true for all values for which every expression in the equation is defined. So that sounds a little weird, but we'll get into what that actually means here in a little bit. They help you to evaluate functions, simplify expressions, prove identities, and solve equations. So we already know all of the ones there in the boxes. The quotient identities, tangent and cotangent, we know that. The reciprocal identities, we know those. The Pythagorean identities, we kind of brushed over the sine squared plus cosine squared is equal to 1. We brushed over that when we were doing parametric equations. And then we also brushed over the fact that tangent squared plus 1 equals secant squared comes from that. Cotangent squared plus 1 equals cosecant squared comes from that as well. We'll kind of review that when we get to it. The biggest thing is we've just got to be able to use those. So first thing that we're going to look at here are using some of these identities to find trig function values. So the first example here says find the exact value of sine of theta if cosine of theta is equal to -4/7 and theta is between pi/2 and pi. So this is actually where we're going to start. We're going to start with that inequality because that tells us what quadrant we're in, which is very important. So we are in between pi/2 and pi. We are in the second quadrant. So we are going to draw ourselves a right triangle. In the second quadrant, the right angle is always formed with the horizontal. It is always formed with the horizontal. We're given the value of the cosine ratio. So cosine is the adjacent over the hypotenuse. Our theta, our angle, is always this angle with the horizontal, like it has been when we did reference angles and all that stuff. So our hypotenuse, that doesn't matter. That always goes in the same place. It's always across from the right angle. The adjacent would be the side here on the horizontal. If this is theta down here, then the x-axis has the adjacent side. Notice I do put a -4 on there. Now, I know side lengths of triangles are never negative, but we are dealing with direction here. Okay, we are dealing with direction. So if we want to find the value of sine, sine is opposite over hypotenuse. So we've got half of that ratio, but we need to find the opposite. Well, that's just the third leg in the triangle, so we're just going to use the Pythagorean theorem to find that other leg. So hypotenuse squared minus leg squared, that leg is the square root of 33. If it is not a perfect square, leave it in square root form. Now, that value is positive because we're in the second quadrant. Y values are positive in the second quadrant. So the sine of theta is the opposite, which we just found was the square root of 33 over the hypotenuse 7. So that is what we're looking for. That is the exact value of sine of theta. Notice, we didn't actually find out what theta was. We could find out what theta is. We could use the inverse, find theta, and then plug it back in. But that's not going to give us the exact value. That's not going to give us the square root of 33 over 7. It's going to give us a decimal. Okay, let's look at another one. Find the exact value of cosine if cotangent is equal to 2 over 5 and theta is between 180 and 270 degrees. So this time we are in the third quadrant. So let's go ahead and draw our triangle in the third quadrant. Label everything that needs labeling, our right angle, our theta. Okay, cotangent. Tangent is opposite over adjacent, so cotangent is the reciprocal of that. That's going to be the adjacent over the opposite. So the adjacent length is 2, the opposite length is 5. Now, we need to add something to these. Both of these should be negative because we're in the third quadrant. Negative x, negative y in the third quadrant. The reason why cotangent is positive is because it's adjacent over opposite. If they're both negative, it's going to turn out to be a positive. Cosine is adjacent over hypotenuse. So we have the adjacent. We need to find the hypotenuse. So leg squared plus leg squared, 29. 29 is not a perfect square. It does not reduce. So we'll leave it as the square root of 29. So the adjacent is -2. The hypotenuse is the square root of 29. The answer may be left like that. It may also be rationalized. So quick little refresher on that. Multiply top and bottom by the square root of 29. Square root of 29 times square root of 29 is 29. If the 2 over 29 would simplify, we would simplify that, but it does not. So we just leave it as is. All right, one more. Find the value of tangent of theta if cosecant of theta equals -2, and theta is between 3 pi over 2 and 2 pi. So here's an example in the fourth quadrant. Okay, cosecant is the reciprocal of sine, so this is going to be the hypotenuse over the opposite. Notice this one wasn't a fraction. Make it a fraction. Put it over 1. So the hypotenuse, now the hypotenuse is never going to be negative. So let's see here, the hypotenuse is 2, the opposite is -1, and that makes sense that the opposite is the negative value because that should be a negative y here in the fourth quadrant. Let's see here, we're finding tangent, so we need the opposite over the adjacent, so we need to find the adjacent side. Hypotenuse squared, well, I don't even need a calculator for that. It's the square root of 3, right? 2 squared is 4, 1 squared is 1, so 4 minus 1 is 3. Square root of 3 is our adjacent side. That is positive. X values are positive in the fourth quadrant, so our tangent is the opposite, so -1 over the adjacent square root of 3. We want to rationalize that. So square root of 3 over 3 is our tangent value, our tangent ratio there. Any questions about those? All right, let's flip over to the back. Now, this is what truly trig identities are, okay? We are going to simplify some trig expressions. That means to rewrite it as a numerical expression or in terms of a single trig function if possible. So it's not always possible to get it down to just one trig function, but as much as possible, we want to try and simplify it. So let's look at the very first one. We've got sine of theta times secant of theta. So one of your methods here should be typically to turn things into terms of sine and cosine if possible. So secant is 1 over cosine. So we just replaced it with 1 over cosine. And then if we're multiplying there, that's going to be, you just multiply straight across the top, straight across the bottom. So that's sine of theta over cosine of theta. And sine over cosine is tangent. So that expression there simplifies to tangent of theta. So what that means is for any angle, if we take the sine of that angle and multiply it by the secant of the angle, that value will be the exact same value as the tangent of that angle. Okay, that's what that means. Okay, let's look at number 6. 2 times the secant squared of theta minus tangent squared of theta. So anytime you see squares, you should be thinking the Pythagorean identities. Okay, so when I look at the Pythagorean identities, I'm going to write this over to the side. Okay, this is not me simplifying. This is me taking the Pythagorean identity, tangent squared of theta plus 1 is equal to secant squared of theta. The question is, can I manipulate this expression so that it looks like what is in my problem? Well, yeah, we can subtract tangent squared of theta from both sides here. So we get 1 is equal to secant squared of theta minus tangent squared of theta. So secant squared of theta minus tangent squared of theta is equal to 1. So we are going to replace that in our expression there with 1. So this simplifies to just 2. So it does not matter, once again, it does not matter what angle we're talking about here. If we take the secant squared of theta minus the tangent squared of theta and multiply by 2, the result will always be 2. Okay, let's look at number 7. Number 7 looks like we may do something similar, but if we look at the Pythagorean identity involving sine squared and cosine squared and cosine squared are already on the same side. So there's no way that we're going to turn that expression into cosine squared minus sine squared. So let's see here. What do we need to do instead? If we want to make this so that it's just in terms of cosine squared or just in terms of sine squared, let's take our Pythagorean identity. Okay, we're not going to be able to completely eliminate it like we just did in the last problem. Okay, but our Pythagorean identity says cosine squared plus sine squared is equal to 1. So since cosine squared is listed first, let's solve this for cosine squared. So that means we're going to subtract sine squared to the other side, and we are going to substitute this expression in for cosine squared. Cosine squared is equal to 1 minus sine squared of theta, and we already have a minus sine squared of theta in the problem. Okay, this is our substitution. And then the minus sine squared was already there. So we have 2 negative sine squared of theta. So it may not look like we have simplified this very much, but we did get it in terms of one single trig function. Instead of having both cosine and sine, now we have just sine squared in the equation. Without any other instructions, that's about all you could do. Now, you could do a similar thing. You could have also solved this for sine squared and plugged it in and had your equation in terms of cosine. Again, without further instructions, it's kind of up to you as far as how you handle that. All right, let's look at number 8. Let's look at number 8. Sine of theta times cosine of theta over tangent of theta. So we've got sine of theta and cosine of theta in the numerator. So how about we write that denominator so that it's in terms of sine and cosine? Yeah. Now we have a fraction within a fraction. We always flip the bottom one and we turn that into multiplication. Okay, so I flip the bottom over, it's times cosine theta over sine theta. So we can cancel the sine of theta, because one of them's in the numerator and one of them's in the denominator. And then cosine times cosine is cosine squared. Okay, let's do one more, and then I'll let you practice with a few of these. Number 10, secant of theta times sine squared of theta over 1 plus secant of theta. All right, so let's see here. How about we start with a couple different things that we could do here. Let's try multiplying by the conjugate. This is a method that we use from time to time. Okay, if we multiply the denominator by that expression, we also have to multiply the numerator by that expression. Okay, let's see here. If we multiply the numerator, we've got to distribute this expression right here. So that gives us secant of theta times sine squared of theta minus secant squared of theta sine squared of theta over, if we multiply out the denominator, we've got to FOIL that. 1 times 1 is 1. The outside and the inside cancel. And then positive secant times negative secant is negative secant squared of theta. That's the whole purpose of multiplying by the conjugate. It's the difference perfect squares, so we're going to end up with an expression like this. Now, 1 minus secant squared is equal to negative tangent squared. That's one of our Pythagorean identities, because tangent squared plus 1 equals secant squared. If we move things over, we're going to get negative tangent squared there. So let's see here. Our denominator is negative tangent squared of theta. Now, I know we just multiplied out the numerator, but because now I've got this tangent squared in the denominator, I'm thinking that it would be helpful if my sine squared was factored out here in the numerator. Both those terms have a sine squared, so I'm just going to factor that out. Because now I'm going to rewrite tangent as sine over cosine. And it is negative. Negative sine squared over cosine squared. This one's a little bit longer than the other ones. Does everybody see what I've done so far? All right, now same deal as in the last problem. We've got a fraction within a fraction. So we keep the numerator the same. We flip the denominator over and multiply. Don't lose that negative. Okay, so our sine squares cancel. And then I'm seeing secant. Secant is the reciprocal of cosine. So I'm going to rewrite those secants in terms of cosine. 1 over cosine minus 1 over cosine squared. And then I've still got a negative cosine squared there on the end. So if we distribute here, negative cosine squared of theta over cosine theta, that's negative cosine of theta. And then a negative times a negative is a positive. Cosine squared over cosine squared is 1. And you'll probably see this just because this is what they do to save ink. You'll probably see that written as 1 minus cosine of theta. So that one took a little